Okay, good afternoon. Welcome back to our afternoon session. Today, I have the pleasure to introduce Arkaitz Rodas. He's a good friend of mine. First time I met him, he came for an internship to JLab in 2018. Later, he got his PhD at Complutense University of Madrid in 2019, and he joined the College of William and Mary for a postdoc position that he currently holds. And he has the honor to become in October a new Nathan Edgar Fellow in JLab. That is the most prestigious fellowship on the lab. So he's going to tell us a bit about hadron spectroscopy and, well, in particular, the quest for exotic hadrons. And, well, as we say, just don't be shy. You can interrupt at any time. If you have questions, just raise your hand. Same with our online audience. Just raise your hand in the Zoom, and we will bring the questions immediately. So the floor is yours, Arkaitz.
Thank you very much, Juan. Well, let me first thank the organizers for inviting me. I think this is going to be a cool set of lectures. So I'm very glad that you guys are very fresh, and this is the second day. You still have lots of energy. I hope not to drain you with energy and then instead of drain you, motivate you to keep looking at this. So at first I thought that I would give a set of lectures. It's going to be just 4 lectures, 2 today and 2 on Friday morning. I thought that we need doing them on the quest for Exotica. So basically talking about exotic mesons in particular. Then realize that you don't have the introduction to PCD, you have introduction to small x and to perturbative expansion, and you don't have an introduction to particles in general, so I don't know what the backgrounds are. And I thought of doing something very trivial kind of for the first couple lectures, so we all are on the same page, and then moving on to exotics for the next couple. So hopefully it's not going to be too dense. You're going to enjoy it. If not, please don't tell me. And then we will have a nice chat. So we'll see me walking around for each other on this. So today we're going to focus on the strong interactions. Not a very cool thought, but I think it's one of the things very well what we want to look at. And we will say a few words about the electromagnetic and electric interactions just because we need them to basically determine things that we're going to measure in experiments. So let's say, because I'm going to do a brief motivation, that you don't really care much about the strong interactions, but you care about bigger questions and you don't want to look at light particles, but other things. Well, they play a key role at early stages of our universe. So we want to understand synthesis or biogenesis. We're going to need to understand them. It also explains us how the cores of stars are stable and how the elements are produced either in stable fusion or supernovas. And also, if you don't care about any of this, and you just want to look for standard physics for the beyond, they basically give us the tools that we need in hadron physics to look for other kind of hidden interactions that we don't know about. So today we're going to be talking about bound, not exactly bound nucleons, but bound hadrons, where the mediator of the force is the gluons. If we were to put a picture, to try to make a pictorial representation, usually we would have a quark and an anti-quark, and in between lots of gluons. So if we were to simulate it or just draw it with an ordinary flux tube model, it would look something dense like this, which means that gluons aggregate between quarks, and then the force is constant with the distance. But it also means that the potential grows linearly with the distance. So in order to split 2 quarks apart, we need an infinite amount of energy. The scales involved here, femtometers, are roughly speaking 50,000 times as more than an atom. So we are very small scales, right? This doesn't happen when 2 particles, like 2 mesons, are split apart. And my very best friend is the pion, which is not as known as the proton for these reasons, but we will play with them because they appear in final states and they populate our final states in experiments. In particular, you're going to have lots of lectures talking about this in detail and digging deep into the internal structure of these guys. For us, this is just going to be the simplistic picture of a balanced quark and an anti-quark with a 1 gluon, no more than that. Okay? So we're going to be talking about the quarks. There are 6 in here. We're going to forget about the top one because I don't like it. And then the gluon. And it's all we care about in the stars. So pretty much like you could do on a lab where you get your source of light, and then somebody asks you, what is it made of? So you are going to split the colors apart, you're going to use some prisms, some diffraction techniques, and then some detector. And at the end of the day, you're going to give me the light spectrum. These are some peaks depending on the colors that the light has. So you can tell me, it has a peak to the green or to the blue, and it's made more of this or that. Now you can do this in quantum mechanics, the hydrogen atom gas, and this is basically going to tell you which are the lines of emission of this atom or absorption, depending on what you're looking for, right? So probably most of you know about this, and most of you have also played with this. So we're going to try to relate that to what we do in QCD. So first things first, if you were to do that with a hydrogen atom gas, and then you compare to what we know about quantum mechanics. Let's say we start by the simplistic Schrodinger non-relativistic equation, and then you get the energy levels. So you have quantized your atom, you know that the levels are quantized, and then an electron basically can absorb photons and get excited, or emit photons when an excited electron drops from one level to the other. And so in doing so, you can test this equation here. Not only can you test it, but if you had utmost precision at determining these levels, then you could also check for possible corrections. Now, we only know quantum mechanics. Let's assume we know nothing about QFT. These corrections are going to motivate the introduction of something beyond what we know about quantum mechanics, right? So if we want to get them right, we start by measuring something and then testing if what we are developing is correct or not. Okay, we're going to try to do something relatively similar for QCD. This is the Lagrangian formulation of QCD. It's just a one-liner. It's fine, seems easy, right? There is only 6 building blocks, remember 5 because I don't like the top, and then the glue. Problem is, we cannot extract information directly from this Lagrangian at the hadronic scale. Interactions between these two guys are too complicated for us to give you a closed formula for how this looks in the hadronic scale. Let's compare it to QED first. So for QED, once again, we have a one-liner Lagrangian. It doesn't look very different from QCD, does it? Now, the first thing that is interesting for us is that we can calculate perturbative expansions in QED based on the assumption, based on the fact that this parameter is small. So if I was to use a perturbative series and I get different terms, right? This one should be much smaller than the first one. This one should be much smaller than the second one. As at some point, I just can neglect these terms, stay with it, or stick to the first ones. And I have a decent quantitative description. We cannot do that in QCD, as we will see. The second thing is photons do not have charge. So they don't see each other. They only interact with charge. They interact, for example, between electrons and protons, but they don't see each other. And this means that our theory is abelian, or the classical limit is going to be linear. This is going to recover into linear Maxwell equations. Now, this is not the case for QCD. First things first, gluons, mediators of force, see color charge, which is basically the characteristic charge of quarks in thermodynamics. But they also carry these color charges. So gluons not only interact with quarks on these vertices, they also interact with each other. So wherever you have one gluon, you can have 400 or 1,000. And it's a matter of seeing if this perturbative series, if this perturbative expansion converges or not. Because if it converges, well, still you have tons of gluons, but you can do something. If it does not, then 1 gluon, 1,000 gluons, and 1,000,000 gluons are identically the same. Okay, so this is this beautiful plot that gives us an idea of the alpha strong parameters, so the equivalent of the coupling in QED that we use for the perturbative series. In this case, it's the strong one. Now, we see that it's running lower and lower when we increase the energy. So if we go to the Large Hadron Collider, CERN, this scales, this alpha is 0.1. It's a small, it's fine. We have a Large Hadron Collider and then we have very energetic beams. Then this thing can be perturbative. And then you are going to have lots of different ways of explaining jets and perturbative series and small x and everything. And because you have lectures that are much better than I am at this, I'm not going to say anything here. You will have lots of lectures here. I'm going to be here. So I'm sitting on top of a proton and a neutron, where the energies involved are of the order of 1 GeV. Remember that the mass of the proton and neutron is of the order of 1 GeV. And the problem is alpha strong is running high, right? very fast, very quick. So it's going to reach a point where we cannot calculate perturbative expansions. This makes no sense. One gluon and a million gluons are one and the same. So we can't forget about that. We cannot go that way. Instead of having ordinary quarks and antiquarks, our blocks are going to be hadrons. We cannot split them apart, and wherever they have color, they interact through gluons, which binds them together. So what we find in nature is color singlet objects, these hadrons. So this process where we go from a one-liner Lagrangian to our hadrons, this hadronization, is a bit complicated to explain, and we don't really have an answer for that. I would like to understand what's the connection and see if we can gather information out of QCD by doing spectroscopy. So pretty much that we are going to relate the hydrogen spectrum, the hydrogen atom spectrum of the lines, with understanding the description of this Hamiltonian possible corrections. We would like to relate the book and QCD. Now, this bar is killing the website link, but this is the particle data group website. Most of you probably know about it if you don't just ask me for the website. Just have to text PDG on Google and you will find it. But the idea is that this book, on top of many other things, thank you, Malte. Wait a second. It's going away.
You can click on chat, close chat, and everything will appear.
Okay. So this is the website. Thank you very much.
Okay.
And so inside this book, we will have tons of different particles collected and classified by quantum numbers and properties. This is a table of mesons. And you know, there are a few hundreds out there. There are many more actually. These are the ones that are determined, that are decently determined. Okay, its masses and properties. No, we know it. So there is like a collection of quantum numbers in here that we will talk about in this and the next lecture, and there is a collection of masses. So what I want to say is that pretty much like a hydrogen atom produces levels because they are quantized, and this is the spectrum of the hydrogen atom. QCD produces levels, and this is the spectrum of QCD. All of this, each one of these, are created by a bunch of quarks and gluons together. And all of them arise from the same, basically the same 5 quarks that we were talking about, and the same Lagrangian, but they are very different. So the idea is, how do we relate one with the other? Can we tackle them down, or can we classify them? Can we learn something from them? So these are, so yeah, I think I'll take, yeah. And this is not just me and my charlatany. So this is included within the long-range plan of our beloved Department of Energy, which states basically that hadron spectroscopy should illuminate the QCD interactions that binds the quarks. So the idea is that establish a connection between this, forget about the top, and then this, which is what we measure in experiments. And here is where we stand at. It's slow, it's complicated, but hopefully. So let's say that you never care about hadron physics. You don't care about the spectroscopy, you don't like experiments. They're complicated and expensive. And you just want to look for the beyond because we already have the Lagrangian of QCD. So you want to build another Lagrangian. One of QCD is already done. So you go and join an experimental or theoretical collaboration that is going to work on beyond standard model searches. And let's go to hot topics. First hot topic, the anomalous magnetic moment of the muon. These determinations in red are theoretical predictions. The blue band is the experimental measurement, and there is a big tension, right? It's 4.2 signals nowadays. Could be about 5 in the future, we don't know. The idea is that in order to determine this with precision, you gotta describe the rho and omega line shapes. And these are 2 of the states that were on that list in the TDG. So you better know about hadron physics and spectroscopy if you want to look for this hot topic. Okay, you don't care about that one. What about probability case? Where there are observables that are in tension with the standard model physics, it should be 0, but it's around here, so it's several seconds away. Well, also, if you want to learn anything about them, you better know about some hadron physics. What happens if you join an experiment that wants to detect dark matter? you are gonna play with protons and neutrons, with nucleons at the end of the day. So you better know something about the pyronucleon signature. We have an expert in the audience, over there, that has calculated it a couple of times, Jose. And he will tell you that you need to know about hadron physics if you want to tackle that baby down. So no matter what, if you care about hadron physics initially or you want to look for the beyond, you better know about these things about the structures. Okay, so in the rest of this first talk, this is going to be a very simple introduction to the foundations. So very simple properties and the features of interactions. So I'm going to start with rules of thumb. Basically, this is true, but I'm not going to prove any of them. The first one, the angular momentum, and I will use J or discrete L, depending on where we are at, is concerned. You only have to invoke that the theory is invariant under rotations, and then you recover this. So every particle that we care about has a well-defined angular momentum. It's a very good quantum number. Now, when allowed, strong interactions dominate electromagnetic ones. So we will dominate photons and these dominate double bosons. Okay? When allowed, because strong interactions carry more restrictions than the others. So sometimes might happen, something cannot happen here, but can happen here, for example. Now, mesons, in general, ordinary ones, are made of quark and antiquarks. But in general, I would say even number of quarks and antiquarks. Baryons are made of 3 quarks in the picture, but we can also have pentaquarks or heptaquarks. So an odd number of quarks. And as I said before, we will forget all the baryons in these talks, okay? So first things first, standard model interactions, all of them preserve the baryon number, and this is 0 for us. So that was quick. We are not going to look into baryons, so this is 0. Second and third, QD and QCD preserve flavor, defines the rest between the number of quarks and antiquarks, and they also preserve baryon. For example, a bi-zero has no flavor. If you remember the quark model description of a bi-zero, but in the balance picture, this will be basically up anti-up minus an anti-down. We will look into that. So it has no flavor. It can decay electromagnetically. And this carries consequences for us in detectors. Now, electron interactions, double bosons, do not preserve this. So basically, a pi plus can decay for a double plus. And this carries also consequences. Now, if we are going to look into the case, we will preserve in every vertex momentums and the energies. And this is going to be particularly interesting for us. We will play with this in the lectures on Friday. So if we have a 2-to-2 process, because most of the stuff we measure and we understand is scattering processes. So 2 particles collide with each other and then produce another 2 particles, or 2 particles produce themselves in the final state. Then we can define what are called demand variables. Can someone tell me why did I say these are, these are invariants. And they are defined this way. So can someone tell me why are these invariants? Why would I use these 3 variables instead of the momentum? They don't depend on the reference frame, so they are very useful for us. Now, the 3 of them, let's say that we don't need the 3 of them. With 2 is enough, because they respect this relationship. And this I leave as an exercise. You don't even need the explicit formula of the momentums to recover this expression. But yeah, these S and T variables that are going to be the ones that we use to define our amplitudes are very relevant for us, you will see. So another rule of thumb, apart from claiming that QCD showcases many unique features, and we'll see in a second, another rule of thumb is that the more phase space is open, the greater the decay. And we're going to do an example of this. So if we have a phi meson has 1,020 MeV of mass. It can decay either to 3 pions or to 2 kms. Sorry, this is kk bar, 2 kms. So which is the mass of the 3 pions together? 520. Which one is the mass of the 2 kms together? It's almost 1,000. So can someone tell me, by this rule of thumb, which of the 2 decays will be greater? The jumping mass from here to here is much greater than from here to here.
When you say that the decay is greater, you mean it has a larger cross section?
Indeed. So which one of the 2 would you think, based on this rule of thumb, would be greater?
I would say the pion triplet.
Yeah, but that's incorrect, because this was a trap. Yeah, sorry about that. But thanks very much. I needed someone to. So the idea is, and this exemplifies the kinds of diagrams that we want in the strain interactions. That decay, and it's true. This is, for example, an idea of learning about the phi meson. The phi meson is built upon a strange and an anti-strange quartz. Okay? Pions are only light quartz. So when we connect a phi going to 3 pions, we can have connected quark lines, right? So one is a strange anti-strange, the others are just light. And QCD prevents us from having quartz changing flavor. So it must be connected through gluons. This is the picture. Now, a phi meson, because it's a strange anti-strange, can be connected to KK bar through quark lines. This is how, for example, we learn about the phi meson. Now, if we can get a final diagram or a diagram, even if it's not a final diagram, something that represents the reaction, we can cut vertically just gluons. Then this is suppressed, heavily suppressed. And this is the OCI rule. This way, one would expect as a rule of thumb that this would be greater than this, but it's not experimentally. And the way of explaining this is this OCI rule, which also tells us that the phi is indeed a strange anti-strange. Because if it wasn't, then it would decay mostly to 3 pions instead of 2 K. Now, this is even more suppressed for heavy mesons. Can someone tell me why this is even more suppressed, this OCI rule, for heavy mesons? Well, the answer is here. This alpha strong runs slower with the greater the energy. So if you have a psi that has almost 4 GeV of mass, and it decays to 3 pions, then the phase space is much greater. The difference in energy is much greater, right? So basically, this alpha strong is lower. So it means that it's even more suppressed because each one of these photons interacts more weakly than before. So is there any question to this point? I'm gonna put some question slides from time to time so I can drink some soda.
So you said the phase space has got something to do with the mass difference?
Right. So the idea is that in order for this to decay to this, right, because energy must be preserved, this mass has to be greater than these objects. If it wasn't, then it couldn't decay. Now, the difference between this mass and this mass is giving you the energy that this carries when it decays to these objects. Or basically, the free energy that these objects carry when this thing has decayed, right? That is the phase space. So the bigger this difference, the more energetic these three will be when they show up out of the decay. And as a rule of thumb, when that increases, then the decay is greater. Depending also on the quantum numbers, and we will speak about that in next lectures, the shape of this phase space increase will be different, depending on the angular momentum in particular. But as a rule of thumb, the phase space will increase because the phase space depends on the momentum of these guys.
Right, so as the phase space increases, that decay channel gets suppressed more.
No, as a phase space increases, decay channels increase as a rule of thumb. Because if you look at the formula of the cross section, it depends on the phase space. The phase space will be in the numerator in that sense. So if one increases, the other increases. This one is suppressed, right? Because it only has gluons mediating it.
But this one has more phase space to cover, right?
Yes, indeed. But let's say the couplings in these vertices make it much smaller. So it has, so as a rule of thumb, because this is why it was a trap. As a rule of thumb, this would be greater because it has much more phase space. But the couplings here, because they are only gluons, is much lower than this connection. What I wanted to, apart from the fact that QCD is very complicated, I wanted to stress the point that for strong decays, we look for this kind of diagrams, not this kind of diagrams. So we want continuous quark lines. Basically, what we don't want is diagrams where we can cut only gluons vertically. So yes, this could be greater the greater the phase space, but still it's suppressed because you only have gluons.
So I understand that the only gluon lines are suppressed, but why?
But why?
Yeah.
Well, for example, you can look at this. So you have, let's put an example with the psi. This is almost 4G. This is 3.77. And this is 500. The difference is 3G, right? If we look at the alpha strong topic here, and the 3G scale, you probably don't see the x-axis, but is here. So alpha strong is 0.2, which means that this value is low. Whereas this other decays work lines are not addressed by any means. So in comparison, one versus the other, this one is great. And if you have like 100 GeV difference of mass, of course, this alpha strong is even slower. So that is why it separates. This is a bit of hand waving, but gives you an idea. Is there any other question?
Why are we ignoring the top part?
Because it's super heavy. And so it means that hadronizes many things, and I don't know how to explain it. So it doesn't create resonances, maybe. It doesn't, in principle, create resonance because it's so heavy that it hadronizes many other products that have so much energy that ends up in a different, let's say, energy scale where you have over effective field theories and ways of describing things. So it's not exactly like lower mass hadron physics. So if you had a top that's 170 GeV, then this thing, when it decays, the products carry so much energy, right, that you are no longer in this region. You are again in this region, right? Because it was so heavy when it came to lighter products. Then most of the energy is just free energy that goes in the momentum. And so it means that it's no longer honest to God hadron physics. It's something that perhaps will be perturbative. Yeah.
So I just wanted to follow up on the questions the students asked. Do I understand correctly that the suppression factor you're talking about is just by powers of alpha S? So
Is yes,
the suppression margin, is it just by powers of alpha S?
5 powers, is it?
No, is it by powers of alpha?
Oh, well, I mean, this is hand wavy, so I don't think it's exactly that way, but it was my way of explaining it. So in principle, if this is, the difference is very energetic, then I think it could look like that. But in this case, I don't think it's just that.
Right.
So this is just very hand wavy.
So there's no parameter that explains why.
I
it's
cannot
suppressed on the
calculate,
left side.
right, I cannot calculate algebraically this. This is a hand wavy way of describing the fact that we can have this kind of diagrams. And I can do an explanation for heavy objects that makes more sense. But for this, it's just hand wavy.
One follow-up question to that.
Yep.
In addition to the number of strong vertices, we're also looking at the mass of the bound system to get an idea of how strong that coupling is.
Okay, can you repeat again? Because I didn't get.
I'm thinking one, in addition to the number of interaction vertices, is it true that another reason why the D decay is greater than the is greater than the pi decay? In addition, because something about the ground state of the D mesons leads to a lower coupling due to a higher Q squared in the ground state.
You mean, so here we're talking about the psi, right? So this, and then you are saying that because of the D meson properties, I don't think I'm getting the full
I'm
question.
trying to understand the relationship to the graph above, where
Oh,
as
right.
we go to
No,
higher
because
Q
in
squared,
this case, because of the quark content of the psi, you could draw continuous quark lines to the 2 dimensions, but you couldn't do it to 3 pipes again. So it would be a similar kind of diagram. So I didn't draw the diagram because I was lazy. But you could have continuous lines to the D plus D minus from a side, but you couldn't have it for example, 3 neutron piles. It would be more or less like this. And so what I was saying is here it would be even more suppressed because the difference is large. So that is the whole argument.
thank you. Let me try to refine my questions
Yep.
then. Is there a contribution to the difference in the decays due to the difference in coupling strength, given the energy transfer Q squared that's required for these two?
Well, yes, of course. I mean, it depends. I mean, the thing is you cannot calculate them depending on the particle. This is heavy, and so you might get some models that describe and write the formula. But as a rule of thumb, these decays and the strength of them will depend on powers of the momentas of the particles at the end of them, which depends on the angular momentums of these objects. It's a basic requirement. So we would go for the 3 piles. And then it will depend on something that, well, it could be a QCD given amplitude that I don't know about, that you can, in this case, for example, plug in a model, and then you could calculate them and get these coupling factors, which I don't know exactly what the numbers are. But the idea is that as a rule of thumb, it depends on the phase space times powers of the momentum. And I'm trying to just made you realize that this is not always the case. It's just a profile.
So when you have heavier masses decay,
Yeah.
if the decay products have the same quark content, they are favored more irrespective of the phase space dominance.
Okay. Can you repeat the question again?
So basically, if the decay products have
Yes.
the same quark content, then they are favored more.
Well, I mean, by saying quark content.
Like in the case of phi.
So the thing is, so the thing with the quark content is that flavor is always percent.
Right.
So that is like, the idea what you mean by quark content is this, right?
Yeah.
It's a continuum set of lights. So for example, here you have an S quark and an anti-S that can go continuously into the chaos. Yes. This is the dominant.
It's the same case over here as well.
Exactly. So this is the case. You could draw something like this for the D plus minus. You couldn't do it for the 3 pi. And this basically tells you that we care about the diagrams, not the ones in front. When the two of them are allowed. Sometimes this one might not exist, but this one might exist. We will see an example of something. Okay. So I'm gonna continue. I still have some slides. But the idea is we started from 5 quarks and 5 anti-quarks. And here I am introducing you a table of mesons that are almost all stable under QCD interactions, and they are 28. So what happened? We went from 5 degrees of freedom to 20. I'm saying these are the basic building blocks for us. This doesn't look good, right? I mean, you don't get a 1 parameter formula and then give me 10 different parameters at the end of the day. This gives me 1. So this basically exemplifies how complicated QCD is in a hadronic scale. And we are going to take a look at the ones that we care about the most in experiments in order to do a spectroscopy. So let's start with the pylons one first. So they are made, and we will play with this in the next lecture, by an up and an anti-down quark if you are talking about the pi plus. It can be an up and an anti-up if it's a pi zero, combinations of up anti-up and the anti-down. The idea with the pi plus, as I said before, is that it decays through W boson. And this is the weakest of the 3 interactions. So it lives for a quote unquote long time. The time, the travel distance that it reaches to the first frame is relatively long. What does it mean? It's charged, so for example, we can accelerate it on a beam, and it lives for a long time. So we don't lose them when we accelerate them on beams, right? So you might want to have them on initial stage of the detector. It could work, you are going to lose them, but it still could work. What will happen with a pi zero? A pi zero, as I said before, decays electromagnetically, and this dominates electron-wave reactions, so the time, the lifetime is way smaller, which means that in its first frame, it lives for like 26 nanometers at the speed of light. This is not good, right? Can you build a huge detector and do everything within 26 nanometers or a bit more than that? But I cannot. The idea in here also is that it's neutral. So it will be very complicated for us to accelerate them because they don't have any charge. But these are very good for final states, for example. Can anybody tell me why are they good for final states? When you have a reaction and they show up in the final state. Why? I mean, it's neutral. Why don't we just say this is standard because it has a half charge? Because it splits into photons very quick, and then we can get these photons inside our detector. So Pseudo is fantastic in final states. Okay, let's move on. And on to the chaos. K pluses or K minuses is basically identical. The idea is that they all decay through electron-wave reactions. So we always have a W, in this case plus, or minus for a K minus, and then a CK matrix element. So the idea is that they live for a long time. Roughly speaking, the time of travel is 4 meters. So again, we can do something with them. We can accelerate them. And they live enough so we can play with them in the initial states of our accelerators. The neutrons are more complicated. So we have 2 Ks, the K0 and the anti-K0, K0R. And first thing is that they mix with each other. They mix with each other because they are not Auger states of a Hamiltonian, okay? Instead, we define our Auger states to be these 2 guys, K0S and K0L. These guys don't mix with each other. And they are called basically K0S because it's short-lived, K0L because it's long-lived. We are that smart. So one has around 3 centimeters of travel distance, and the other one has around 15 meters. But there's a huge difference, right? So can anybody tell me which one do we want for the initial states in our detector? Anyway. Okay. We want the K. Now, do we want any of these two in the final states of our detector? Indeed. So the Ks are also decayed pretty much like a pi zero into products that we can measure. So that's fine as a final state. But the K long is not charged and it's very long. So it's cool on the initial states, but on the final states, it would fly past through the detector. So we won't see anything, right? So we don't want these guys in the final states. We want this guys. We want this in the initial states. Now, the masses are different, and we are going to see a cool phenomenon. And this means that a K0 and a K0 bar are going to oscillate between one and the other because they are made of K longs and K0s. In principle, if we see the temporal evolution of a K0 state, let's say that I get a K0, I let it evolve over time with the Hamiltonian, and then at some point calculate the probability that this K0 is still there, then we will have this formula. And what I can care about most is the mixing there, because the masses are different. Now, I don't have a cool plot about the mixing of neutral kaons, but I do have one for the P measures. And then, no, they are not called values, okay? The idea is that pretty much happens for B0 and B0 bar. And this was measured by LCD. And you can see with which precision it is measured. So this does happen indeed. And we can see that all these things work, right? Makes sense. So now we have the full list of 28 measures. And the problem is, this is just the beginning. I didn't even start talking about variables. And these are just, let's say, the stable ones. So what this is going to happen when we start adding variables and they're stable and everything, we're going to have thousands of them. So we're going to start packing them in, well, basically in groups by using symmetries, right? Symmetries are good, and QCD has lots of those. So I wonder if, you probably have seen this already today or just today. Yes, you have seen it. I just got the double check. So first things first, if we get the QCD Lagrangian, and we focus only about the direct part of the Lagrangian, we will see that it depends on the mass of the quark. Doesn't depend on anything else, right? So in principle, if the masses of the up and down quarks, let's say, that are the same, then one would expect this Lagrangian to be invariant under rotation between one or the other mixings between them, right? Well, it turns out that the masses of the two quarks are much smaller than the ones of the hadrons. So this is a very good symmetry. And this is called the isostate. Because we have a two-level state, right? We have one half system, and it has an up component and a down component. Once again, we are very original with names. And so we can define the isospin numbers. And it's going to be a very good quantum number for us. In particular, we are going to use the third component of the isospin a couple of times. Remember, final number is 0 for us. And most of the time, examples of them going to put the spin is also 0. So the third component of the isospin of a meson, in most cases, in my examples, will be just the charge of a given meson. So with this, we have up anti-up, and down anti-down, and we could in principle mix 4 different mesons with them, right? We're going to recover with that 3 pions and sum, and I'm not going to go into that sum. Okay, let's make everything slightly more approximated. So let's say that the strange quark mass is also much smaller than hadrons, which is true. At the same time, it's much bigger than the mass of the light quarks. So this symmetry is just going to be approximate. Now, if we have 3 different flavors, and a meson is made of a quark and an anti-quark, how many mesons can we build with this? 3 times 3, right? So in principle 9, which could be described as 8 plus 1. And I forgot to put the figure. So here I'm showing you 8 of them, which is the octet. And then I am not showing you the knowledge just because I took this picture from Wikipedia. And this also happens for baryons. In the case of baryons, how many would we have? in a multiplet. In principle, we have 3 quarks per baryon, and each one of these can have 3 flavors. So it's 27 of them. And then we put the students in the symmetry groups, right? The idea is that because this is approximated, it's an approximated symmetry, but because it's decently approximated, then the masses, compositeness, and sizes of the software, one would expect that naively speaking, they are related. Okay? So let's take a look at how we build them. And let's do an exercise. I said before what the pion is made of in terms of quarks. Let's take a look at it. So what is the charge of a pi 0? Anybody? 0. What is the baryon number of a pi 0? And the spin? 0. So the third component of an isospin is 0. And this is the table of Cleb's coordinates, and now this thing is in the middle. But I promise you there is a 1, 0, and 0, 0. Let me see, I can do this myself. So if I click on it, am I gonna break something?
No. Just
Click on the X.
on the X.
Okay,
That's fine.
fine.
Might need to click one more time to make sure you can use the.
Yes, good idea. Oh no, I could. Yeah, you saw the solution. Okay. So we see here for the Cleb's coordinate table that probably most of you played with. So we have a 1, 0, and a 0, 0. The lower column is the lower row is the third component of the isospin, which we already determined here. What about the total isospin? What is the total isospin of a pi? Is it 1 or is it 0? 1. There are 3 pions, so it has to be. Okay, so this is the state of a pion made of quarks. So we are going to have the terms, and because we have to use square roots wherever we see these numbers, is 1 over the square root of 2 up anti-up plus 1 over the square root of 2 down anti-down. So the solution is, wait, it's a minus there. Why is there a minus there? Because I defined the anti-down this way. So there is a minus there filtering. Okay, so we know more or less how to build our basic blocks, or at least how to take a look at the word picture of these basic blocks. We will take a deeper look into the quantum numbers in the next lecture. So in order to finish this lecture, we're going to go slightly into something that I find very interesting, but it's kind of going to be useless after I introduce it, because we are never going to mention it again. But it gives an idea of the masses of these quarks, of these mesons, sorry. So as I said before, because the masses of these 2 quarks are very close to 0, the Lagrangian, if they are 0, identical to 0, then the Lagrangian is invariant under chiral rotations. And this is called the chiral symmetry. Now, I also checked that you have already seen conserved currents and the Noether theorem. So this means that we're going to have some conserved currents associated to the fact that the Lagrangian is invariant under a given rotation and symmetry. So in principle, we're going to take a look at this, at the axiom. Okay? So the problem is, okay, Lagrangian is invariant, but our ground state is not. Our ground state is not made of a quark or an antiquark. Our ground state is made of hadrons. So the Lagrangian is invariant, but the ground state is not invariant under the same symmetry. And so it means that this symmetry was spontaneously broken. You probably have seen the picture of the Mexican hat potential. And I know it's used everywhere, but they have an old way of explaining it. The idea is that the ground state went from metastable to something stable that doesn't respect the same symmetries that it had before. But the Lagrangian is invariant under this symmetry, which means that these charges are conserved and they commutate with the Hamiltonian of QCD. Because it commutates, this relation is 0. And acting on the vacuum, of course, is 0. This my construction is just this. This part is Hamiltonian acting on the ground state, so that is identical to 0. So we end up with this term, which is basically the Hamiltonian acting on the charge is conserved on the ground state. So there can be 2 things. Either this Q annihilates the vacuum, as it means that the ground state is also invariant under this symmetry, or it doesn't, which means that it's not invariant under that symmetry, but the Lagrangian still is. So if it doesn't, then it will produce something. it will produce something with these quantum numbers. And these quantum numbers are basically angular momentum 0, a negative particle. So it's what we call a pseudo-scalar. But then, if it doesn't, because this relation is still true, the Hamiltonian must annihilate these particles, which means they are massless, right? They are eigenstates with mass 0. So we basically got a set of particles that have these quantum numbers, pseudo-scalars, which mass should be 0. And they are these guys. Now, you tell me, no, the pions have mass. No, no. This is true because the symmetry is also explicitly broken. The masses of the quarks are not 0. So the chiral symmetry in the Lagrangian is only approximate. It means the greater the mass of these quarks, the more broken the symmetry is. And so the more mass these objects will acquire. If the masses of those quarks will be 0, then the masses of these guys, of the pion, kaon, and eta, will be 0. So now, why do we have this difference in mass? So the pion is very light, okay, it's roughly speaking 6 times, 7 times lighter than a nucleon. But why is this guy much heavier than a pion? I just made an argument and I call them all, these pseudo-goldstone bosons that are called. But why is this 3 times the pion? Why is this also 3 times the pion? The answer is because this one only contains light quarks, which break the symmetry. It's a very little breaking of the symmetry. But these 2 guys have a strange quarks inside, which have a much bigger, much greater breaking. And so there is a relation between the explicitly broken symmetry and the masses that they acquire. Now, it's also interesting to see that even if it's for different reasons, this hierarchy stays in all these kind of multiplets. So I introduce you to the multiplet that we'll discuss in the next lecture, which is the vector measurement. And the idea is that if we look at particles in this multiplet, these 4 here, that only have light quarks, I promise you, they only have light quarks, then their masses are very similar, right? But now if I look at something that decays star, this guy has greater mass because it has 1 strange quark. And if I look at the phi, which has 2 strange quarks, then it's even greater. It's an approximative theory, and the idea of classifying them doesn't give you the exact same answer because there is a 200 or something the difference in mass. This is only 1/4 of the total mass of the system. So it's a decent approximation, right? And so I'm going to stop here, and we'll go into details about this vector measure multiplet in the next lecture.
Well, thank you very much for this amazing lecture. Arkaitz, questions from the audience?
Yep.
So you talked about the Mexican hat potential, right?
Yep.
So for the excited states, it preserves chirality.
Yes.
Yes. Now on the ground state, the chirality is broken, which means this Mexican hat essentially tilts to a different equilibrium point.
Yes. Maybe, yes. Well, yeah. I mean, so this also was taken from picture reviews and a description of the linear sigma term model where you only have these states as the constituents. So that's also what you see full symmetrical order.
My point being, when it becomes the ground state, the Mexican hat actually tilts.
It has to. So the idea is that this Mexican hat, if I don't get it wrong, you will have some moment. It's never going to be exactly like this. First things first, all these modes have acquired mass. So the ground state won't be exactly like this. This rotation is not going to be like this. It's going to be full symmetrical. Otherwise, they would all have the same mass, and they don't. So, and then also the modes that acquire mass here, they don't have the same mass. So there is also a difference between that. So it must not be exactly that symmetric. This is another simplification. Because I mean, if it was like this, then these pion modes, let's say that I put the whole multiplet in here, then all of them would have the same mass, and they do not. So there must be a difference between them. More questions?
More questions? In the back?
Yep.
Can we compute the mass of the middle by only using the quark mass? There is a formula? Or?
Yes, so for the people online, so they are asking if we can compute the mass of a meson, by just using the masses of the quarks, if there is a formula, and there is. This is an effective in theory. So you will describe it with a pinch of salt, but it converts decently well, I think, for the mass of the quarks. The idea is that you are going to have a parameter that relates basically the masses of the quarks, the quark condensate, to the masses of the pseudo-goldstone bosons, and you will recover a parameter that at tree level can be related to, for example, the decay constant of the pion, and then a higher orders it must be fitted to data. Okay? And also, yeah, that's right. So another interesting thing that I didn't say is that the masses of these guys depend on the masses of the quarks. So for example, how would you expect the mass of an ordinary meson to depend on the mass of the quarks? We have a quark and an anti-quark. Do you expect it twice the mass of a quark? Do you expect it Q squared? Yeah, but if you were to relate the two equations, let's say that we have a phenomenological formula that relates the two. So would you expect it to be linear? Would you expect it to be quadratic? Linear. So linear is what happens for these guys, but in some quite model calculations, you can see that for others it's quadratic. So these are slightly different than others.
What would be the reason why K-longs and K-shorts have different masses?
Oh, I mean, in principle, they can have different masses. The quarks, the light quarks that are inside are not exactly. K-longs and K-shorts are made of K0s and K0 bars, right?
Right.
So it's not a simple of a picture, but let's say that we have a K0 and a K0 bar, or K0. Let me go here. So then we have here. Well, so the idea is that you have different mixing between these guys, and so in principle, if I'm not mistaken, no, I mean they have the same light quark. So I really no, the argument that I was about to make doesn't make much sense. So they are allowed, and the argument that I was, the simplistic argument that I was about to make, doesn't make much sense. So I'm just going to stop here.
I know the argument.
Yep.
The mass difference is incredibly small.
Yes.
Due to the weak interaction.
Okay, that's a good point.
And it is actually higher order in the weak interaction. So it's because like G30 squared. So for that reason, it's an incredibly small.
That's right.
Is that like experimentally measurable, or is that just like?
Yes. You
Okay.
can,
The method to measure it is that you have a K-long beam, and then it goes to a material, and the interaction with the material, even if it's rather weak, allows to regenerate the K-short. Okay, so yes, they say that the weak interaction between the K-long and the eigengraph, okay, makes that the eigenstate is no longer the K-long, but now it's a mixture.
so is something related to this
There is a
formula?
way to extract from that cross section.
So is it something related to the formula that gives you the temporal evolution of a K0?
And yeah.
I mean, in principle, you could.
The width of the lifetimes are a little bit.
Oh, the lifetimes are different.
Because the K-short, the case is 2 pi, actually the K-long, the case is 3 pi. So this calculation of that whole race is actually one of the problems that people look at that discussion.
So the idea is that the K-short and K-long are CP eigenstates, right? So that's why they decay to different things. And the strong interactions, you cannot mix them because the strong interactions per se is CP.
It's interesting because you said that like K-shorts decay to 2 pions and K-longs decay to 3.
Yeah.
So then in the argument earlier, when you were talking about like the amount of phase space dictates the rate of the decay, why then would K-longs take longer?
Oh, CP. Probably it's just because of the city numbers that each one of these has.
We have a question here.
Oh, yeah.
Go ahead.
So when you're showing that like diagram that had like all of the different mesons on it, like the different combinations.
The table, you mean?
Or no, this was further on towards the end.
Okay. You have that.
Yeah, that one.
Yep.
So this isospin only holds, like, assuming we're working at high energies where you can kind of treat, or does this only hold at like high energies where like up, down, and strange are kind of considered like the same like mass eigenstates
Okay.
of or because
So I see your point.
Because what I was gonna ask is, is there another way to like formulate this where you could include like charm or bottom, like if you were at like high enough energies, or are those just too massive?
I mean,
to
you can
really-
approximate that. So the thing is, when we are looking at hadron physics, right? By definition, the scale is 1 GeV, because otherwise you cannot produce hadrons, roughly speaking, right? All of them have that mass. So 1 GeV is already much greater than these two masses, because these are like a few MeV on the MS scheme, you know, the MS bar scheme. So the idea is that because it's already much greater, when we play with hadrons, this is already effectively respect. If you were to include, let's say, a charm, then the scales really have to go to so that its symmetry makes any sense. And that's the idea. It's a scale where you no longer have hadron physics, you have a perturbative QCD description. So the objects that you have there is not a different table with much more massive objects. You have some perturbation theory.
And building off of this question, this got less than 5 years. Building off of this question, what if you didn't impose that you were just trying to rotate one particle into the other, but you didn't leave, say, the length of the vector constant either? So it's like rotating and stretching to. Are there any attempts at doing that to account for?
Well, the idea is that I get this right. So what is it? I mean, this invariant and these rotations, right? So what you are describing, when you have this space where you have all unit vectors, because you are describing the rotation between two bases, between two elements of base, is not something that could give you. So to say, it's not anything that would give you a different kind of particle system. So it's only variant for that rotations, and it only makes sense that you do rotations over that system.
But there's no, you can't widen the class of transformations to allow for not just the rotation, but changing.
Because when you change the distance, what is that kind of distance that you have in mind? It's not the distance between quarks. It's not the distance between the system. That is what I'm saying. So for example, let's say that you don't have a unit vector, right? So instead of like having an upward, then 1.3 upwards, this is what I'm asking.
Oh, okay.
So this is what you end up with. You don't have unit rotations.
In my,
And this is not a physical system. It's not something that gives you, let's say, a unit that you can really do any observable or anything, right?
okay, thank you.
At the end of the day, most probably because of how the Lagrangian is built, those things just don't make any sense. It must be invariant and the unitary operations, but the rest of the operations that are not unitary don't make sense in the Lagrangian. And so this unitary means that it's a unit vector. You can see that also in effective theories. In this sense, I mean, unitary mean, for example, it's well, I have it for the next lecture, but this kind of is rotations.
Before continuing here with questions in the room, I would like to know if there are questions from the remote audience. Please feel free also to comment questions or raise your hand. We continue in the room. We can get some more questions. Matt, have your raised hand.
Yeah, I was going to ask this maybe offline, but I guess if we've got a moment now. Can you remind me please why the D bar is defined with a minus sign, but U bar is not? This resulted in the ISO triplet changing sign to look more like an ISO singlet sign?
Yes, well, I think at this point, so to be honest, I always play with this being a positive sign, but I didn't pay much attention. I mean, when I was using this, I was using a textbook. That's why I decided to go with the yeah. So this is also why I reminded it, because there's a minus sign because this is the final way.
Okay.
Always very trouble. Yeah.
Well, if we don't have more questions, maybe it's a good time for the break. Well,
Just one announcement. There seems to be, there was a little bit of confusion about the channels on Slack. We always mention channels here, channels there on Slack. All the channels are public, but doesn't mean that they are upfront in your Slack list of stuff of channels you are subscribed to. So you have to subscribe to a channel to receive the notification and to see this in the list of your channels. It means in principle, you need to press a plus, browse the channels, all the public channels you can subscribe to what you want. For example, this lecture, for example, the intro to QCD, for example, the social, for example, the seminars channel and stuff like that. So to cut things down and the possibility of misunderstanding, Malte will subscribe you to all the public channels, and you're free to unsubscribe yourself if they bother you. Okay, but he's gonna subscribe you automatically to everything possible available so far, and you're free to do whatever you want. But so don't be surprised if your phone starts pinging. Okay, I'm done.